thank you for coming to our seminar today. Our speaker today is Rudolf Zeidler from Germany, from Münster and also Göttingen. So Rudy is going to tell us about scalar curvature comparison via the Dirac operator. So please, Rudy.
Yes. Yeah, so thank you for the invitation to the seminar and thank you for organizing this. It's very nice to come together with you here. So yeah, as I said, the title is Scalar Curvature Comparison by the Dirac operator. So this is, I guess, maybe more of a Riemannian geometry talk to some extent. So let me start very slowly. So we have some ideas of what curvature is supposed to mean. And usually we have a like two-dimensional picture in mind. And we know that negative curvature should mean something like this. If we have something flat, then we imagine like a flat cylinder maybe, or a flat plane. And that's the sort of case that I want to focus on. If we think about positive curvature, then we imagine something that like closes up and comes together again like the sphere. And that's something two-dimensional. And we want to study higher dimensions now, and their curvature is more complicated. So just as a quick reminder, what kind of curvatures do we have? So we have the sectional curvature, which is kind of the higher dimensional generalization of the Gaussian curvature, which now is not just one number, but gives you one number for each two-dimensional direction in the tangent space. And if the manifold is very high dimensional, this might be very complicated. So there's a lot of numbers. So you can take averages to make this simpler. And sort of the first procedure that's usually done is to consider so-called Ricci curvature, where intuitively speaking, what you do is you fix a unit vector and then you average over all the possible two-dimensional planes that contain that unit vector. And that gives you a new number. And that's the Ricci curvature associated to that unit vector. And then you can take this process one step further and average once more and like average over all the possible two-dimensional directions. And then you end up with scalar curvature. And that scalar curvature is sort of the main player of this talk. But unlike in the two-dimensional situation, this number you get does not like completely determine the local geometry anymore. So in high dimensions, that's very weak, and it's kind of not so clear what that should mean geometrically. But in like geometry, we like to have some connections between curvature and sort of more concrete things about distances, volumes, angles, and things like that. And that's kind of the sort of content of classical comparison geometry. Let me just mention one particular fact that concerns Ricci curvature. And the fact that I want to mention is the diameter comparison theorem, the classical diameter comparison theorem of Myers. So maybe as a setup, if the sectional curvature is bounded below by some constant, then the Ricci curvature is bounded below by some other constant where you get a factor of the involving the dimension. And the scalar curvature then is bounded by this other constant where you get another factor involving the dimension. And from now on, I'll like to normalize everything to this number equal to 1 and state everything I do for this. Of course, you can rescale everything you do and get back to whatever you want. And now, if you do that, the sort of classical result of Myers, which I guess the way I stated it here is goes back to this date, but for sectional curvature, this was known much earlier. So in fact, this probably can even be attributed to Bonnet in the 19th century to some extent. And the statement is that if the Ricci curvature is bounded below by n-1, which is precisely the Ricci curvature of the standard unit sphere, because there the sectional curvature is 1, so the Ricci curvature is n-1. And then the diameter of this manifold is bounded by pi, which is, well, in fact, also the diameter of the sphere. Okay, so that's the result, or that's the sort of a classical statement. And the question I want to start with now is, what about scalar curvature? Can you do something similar or something related like this for scalar curvature? And sort of the first thing to notice here is that there is no obvious diameter bound. Why is that? That's sort of a very trivial example you can consider. Take the sphere and take it at least a two-dimensional sphere and take the product with the real line. And then you just take the product metric where you put the round metric of the sphere here on this factor, and you take the Riemannian product with just a standard flat direction here. And then what happens to do the scalar curvature is that since by definition of this product metric, all the planes that involve this direction and a direction here are going to be flat. So in the scalar curvature, which was kind of the average of all the possible planes, these terms drop out. So only the terms involving the scalar curvature of the sphere remain, and that is positive. And then if you want to get the same kind of normalization as the n sphere, where here you start with the n-1 sphere, you need to put some constant, but of course you can do that if you want to do that. And then you get a metric on the sphere across the real line, which is complete, has scalar curvature, well, in fact, equal to n times n-1. And however, the diameter is infinity. So that just tells you that because you average too much, this notion of curvature is just too weak to control the diameter. All right, so far so good, but now we can analyze this example a little bit more and see what happens if we replace the manifold here, the sphere, by some other manifold. And so the question is, can you always find such a metric on M cross R? So it might be that you could always do that, perhaps. And I guess there are like two cases to distinguish now. And sort of the first case is that M does admit a metric of positive scalar curvature, call it H. Then you can do the same idea, the same construction. You rescale this metric and you just take the product and you get some positive, something positive on M cross R. And if no, then it's more interesting. And then you can, however, try something else. So not all is lost. Just because you cannot do this easy construction, it doesn't mean that it might be not possible at all. So the first idea that might come to mind is to take a generalized kind of product, a so-called warped product. So what is a warped product? So a warped product metric is also a relatively simple-minded construction, but it is very powerful. So you start with some, again, some Riemannian metric. And now instead of taking the product with where you rescale it for constant, you rescale it with a function that depends on, let's say, some interval coordinate. And then you get a new Riemannian metric if that takes values in the positive numbers. And to make formulas easier, it's usually nicer to write a square here. And then you can try what happens to the scalar curvature in such a situation. And you can open your favorite book on Riemannian geometry and you will find some curvature formulas. And in this case, these curvature formulas are relatively simple and they only involve an ordinary differential expression involving the scalar curvature of this metric that turns up here. The function that of course turns up also here, and yeah, you get derivatives of the of the function. And it's quite convenient to write this formula like this. And notice here, this is actually a differential expression that involves the logarithmic derivative of this function phi. And now, I guess this box here already spoilers what I want to say. Now you see we get a problem if we want to do that, what we wanted to do before. So if our goal is to make this here positive, so if this is the goal, then you can observe that it's in fact not enough to rely on this expression here. So you can convince yourself that in fact you cannot find any non-constant smooth function, differentiable function phi, such that this expression here is positive or not even non-negative everywhere. If you want to have it defined, so the problem only occurs if you want to have it defined on the entire real line. And the reason for this is that if you look at this, this very simple exercise using involving ordinary differential equations. So you look at this logarithmic derivative guy here, and if you assume this to be non-negative, you get this differential inequality, and then you can compare that using the exact solution, using the solution of the sort of equality situation here, and you will see that if it's non-zero, then depending on the sign, it will go to plus or minus infinity in finite time, in either in the positive or in the negative direction, depending on the sign. And this is follows from trying to solve this equation just using separation of variables. So you see that this kind of naive approach doesn't work to give you a, let's say, positive scalar curvature metric on M cross the real line if you didn't already start with something that's positive here. Yeah, of course, you can take it constant and this completely drops out, and then you're where we are. You're at the same place where we were before with just rescaling to constant. Okay, but what you can do is, if you sort of drop the dream to have that defined on the entire real line, you can actually get it uniformly positive for some time. So you can solve this equation here where you set this expression here equal to a positive constant, and you can solve that and you will have a solution for some finite time. And you can do that explicitly and you get an exact solution. So let's set this expression here, this expression we had here, set this equal to our favorite constant, n times n minus 1. And we can solve that. So this is, again, an exercise in ordinary differential equation. And if you, let's say, put the initial value phi 0 equal to 1, because you only the logarithmic derivative here matters, it's not so relevant what the normalization is. But if you do that, then you get this formula here. So you get a certain fractional power of the cosine function, and you have it rescaled to the interval minus pi over n to pi over n. And you can solve that explicitly by, I mean, of course, if I give you that formula, you can just check it, that the solution, that it satisfies this equation. But if you want to solve it by hand without knowing this formula, you can also do it. And the trick is that, again, you look at the logarithmic derivative, then you get a first order equation you can solve by separation of variables. And then you're in this very nice situation where you some point realize that the antiderivative of the Arcus tangent is somewhere, and then you know what to do. And then you arrive at this formula, and then you get back to this formula by involving this procedure. All right, and then maybe summarize what we have sort of learned from this kind of elementary experiments. So what we sort of learned now is that if we start with a metric of, say, 0 scalar curvature, let's suppose we have that. So that's sort of the next best thing. If we don't have a positive scalar curvature metric, we might have a scalar flat metric, which then actually must be Ricci flat, but that's at this point not so important. So then we can construct a warp product metric on M cross some interval, which has constant scalar curvature n times n minus 1, and it lives on an interval of length 2 pi over n. And this is kind of a cartoon drawing of this. So you see in high dimensions, if you want to have the sort of same normalization as the scalar curvature of the n sphere, you have less and less time when the dimension goes up. Okay, and now we come to a recent question or conjecture of Gromov. So Gromov basically conjectured that if you have a manifold which does not admit a metric of positive scalar curvature, then this is basically the best you can do on a manifold of the type M cross interval. So the conjecture is that if you have a closed manifold of dimension not equal to 4, I would say something about why you have to exclude 4 here. And you assume that M does not admit the metric of positive scalar curvature. Yeah, does not. And you now take any Riemannian metric on M cross the interval. Yeah, not necessarily a warped product, just any. This could be much more complicated. And you assume that the scalar curvature is bounded below by n times n minus 1. And then the conjecture is that the distance between the boundary components of this manifold here, if you measure it using this metric here, must be at most 2 pi over n. Yeah, so this is precisely the distance that we sort of arrived at by this experiment, using these experiments with warp products. Okay, this is sort of the first conjecture that was stated by Gromov relatively recently, 2 years ago, in his metric inequalities of scalar curvature paper. I'd like to mention two, or I guess one or two other conjectures which sort of fit into this picture and which are a lot older, and they I think the first literature appearance I found was in a survey article of Rosenberg and Stolz in 1994. But I kind of suspect that these conjectures and also this other question, that also this question here, they probably they were kind of around at Gromov-Lawson's time, or like the time of Gromov-Lawson's articles in 1980s, I suppose. But at least there were some results on this already. So here the conjecture is that, again, you're in the same situation, that if you have such a manifold which does not admit positive scalar curvature, then the manifold M cross R does not admit a complete metric of positive scalar curvature. So this is also, again, suggested by these experiments before. So you would, just with a warp product, you cannot do it. And now the conjecture is you cannot do it at all. And also, which is also a companion here, is that on M cross R2, you cannot find a complete metric of uniformly positive scalar curvature. R2 itself admits, if you look at this graph of a paraboloid, then you see that it admits a metric of positive scalar curvature, but not of uniformly positive scalar curvature. For that reason here, the conjecture is only that you don't have uniformly positive scalar curvature. And now, maybe as a sort of first evidence or first example, all these conjectures, in fact, hold for the sort of favorite example, or maybe one of our favorite examples of a manifold which does not admit positive scalar curvature, namely the torus, or more generally for so-called enlargeable manifolds. So in the case of these conjectures I mentioned here, this is in this 1980s article of Gromov-Lawson, already proved there. And in the case of the Swift conjecture, it's much newer, or this was considered in this metric inequalities article from 2 years ago. All right. Now, let's see what we can do further. So, of course, in order to test this conjecture or this conjecture, we need to find manifolds which do not admit positive scalar curvature. So I maybe should say a little bit about how to get such manifolds in the first place. So there are a couple of methods. So maybe sort of something very simple. In dimension 2, you have the Gauss-Bonnet theorem, which tells you that if the Euler characteristic is negative, you cannot have positive scalar curvature. So this is easy. So only for the orientable case, only the sphere remains. Then there's something much more intricate, which only works in one particular dimension as well, and that's Seibert-Witten theory in dimension 4. I will not say much about this, but I want to mention or have to mention it because this is the reason that we have to exclude 4, the dimension 4 for M in all of these conjectures because there are in fact counterexamples to them in dimension 4. So there are some subtleties here. This tells you that this question might be a little bit subtle because this actually false in one dimension, or it's not false for all 4 manifolds. So there are also 4 manifolds where it's true, but there are 4 manifolds which don't admit positive scalar curvature and where this conjecture is not true. But then going into sort of more general dimensions, there is the Shane-Yao minimal hypersurface method. This is in sort of all these cases where this method applies, Gromov in his 2018 paper proved that the Wirth conjecture holds more or less. And in particular, this covers the torus. There is, however, and there are some issues with this, and the sort of most general, or sort of one of the sort of restrictions here is that you need topologically non-trivial hypersurfaces. And in order to have that, by Poincare duality, you need to have a non-trivial first cohomology. And it needs to be sort of sufficiently rich in order to apply this method. So in particular, you can never have simply connected manifolds where you can apply this method or this approach that was mentioned back there. And now we sort of come to the main player of this talk, and that's what we also are most familiar with in a non-commutative geometry seminar. That's the index theory of Dirac operators, of the spin-or-Dirac operators on a spin-or-Dirac operator on a spin manifold. And that, in sort of contrast to this, contains also obstructions to positive scalar curvature on simply connected manifolds. The sort of only restriction, or sort of the restriction here is that you need your manifold to be spin, and need a spin manifold to apply this method more or less. Sometimes it's or usually it's enough to have the universal covering to be spin or something like that, but you need some sort of spin condition. And sort of the main theorem as a spoiler of this talk is going to be that Gromov's Wirth conjecture holds in the cases where you have an index obstruction. Okay, so what is this index obstruction? I think we know this, but maybe just very quickly. So if we have a closed spin manifold, say, then we have a very nice elliptic first order differential operator, the Spinor-Dirac operator. And as such geometric Dirac operators always do, they satisfy a certain kind of Leibniz Weizenberg formula. And in this particular instance, this is called the Schrödinger-Lichner-Rovitch formula, which relates the scalar curvature to the Dirac operator. So the square of the Dirac Laplacian is the connection Laplacian plus a scalar curvature term. And now there are sort of two important things. Is when we apply index theory, then we see that the Fredholm index does not depend on the choice of the metric. And if you combine this with this formula, then you can conclude that if the index is non-vanishing, then M does not admit a positive scalar curvature. Because you can compute the index with any metric, and if it's non-zero, and then if you take one particular metric, it's still non-zero. But if this term here was uniformly positive, then this tells you that this operator must be invertible and cannot have an index, and you get a contradiction. And sort of that's the sort of the general argument. And there's many variations of this index invariant. Sort of the classical one that was first used by Lichner-Rovitch together with the Thiele-Singer index theorem to get positive scalar curvature obstructions is just a basic index viewed as an integer. Then this can be computed by Thiele-Singer, and it's the A hat genus and some differential topological invariant. And that's an obstruction. Then this can be generalized to an invariant that lives in real K-theory of the point. This for scalar curvature was first used by Hitchin. And then even more generally, you can twist your Dirac operator with the sort of universal flat bundle, which is a bundle of Hilbert modules over the group C-star algebra of the fundamental group, and then you obtain the so-called Rosenberg index. And this is still a nice index for which sort of this implication here holds. And sort of that is kind of the most general index obstructions to positive scalar curvature on spin manifolds that we know. And these kind of invariants, maybe just some examples to know what they can do. So for instance, in the simply connected case, this Hitchin invariant here is actually enough to completely classify the positive scalar curvature existence problems in high dimensions. So if you combine the results of Gromov and Lawson and Stolz, it follows that in starting from dimension 5, M does not admit the positive scalar curvature metric if and only if M is spin and the alpha invariant in the sort of KO, sort of the KO version of this alpha invariant is non-zero. And that applies to simply connected manifolds. And here, this actually includes some exotic spheres in starting from dimension 9 and 10 in sort of this parity modulo 8. So there are some exotic spheres, which is quite interesting, that satisfy that they have a non-vanishing alpha invariant and therefore don't admit positive scalar curvature. And if you now bring the fundamental group into the picture, you can, for instance, see that there's just a selection of statements, but one very important fact is that if you have a metric of non-positive sectional curvature, for instance, take the torus, then this kind of refined invariant involving the fundamental group is non-zero. Also, if M is enlargeable, this also holds in this case. This is a result of Tanke-Schick. And this is, I guess, a generalization of this. And another generalization of the first statement is that if M is spherical and the fundamental group satisfies the strong-Novikov conjecture, then sort of more or less by definition, this index will be non-zero. And there is sort of, maybe as a warning, it's however not the case that in high dimensions you can get the same result like this. If you have a fundamental group, there it's a little bit more subtle. So there are in fact manifolds, even spin manifolds, which do not admit positive scalar curvature, but this invariant is still zero. So here, unlike the simply connected case, this invariant does not capture everything. Okay, so this was a preparation, just some ideas as a reminder what this index invariance can do. Now I can state the main theorem that I want to talk about today. So the statement is the following. I will first read the statement and then make a drawing to make it more clear. So the statement here is this: you have a complete Riemannian spin n manifold. You have a compact two-sided hypersurface, and you take some number d, which is smaller than this sort of critical number 2 pi over n that we had before. And you assume the following. So first of all, I want that the fundamental group, sort of the inclusion map of M into X, and uses an injection on the fundamental group. And now I want the Rosenberg index of this submanifold M to be non-zero. So this should be a closed manifold, so this makes sense. And I assume that the scalar curvature is bounded below by our favorite constant n times n minus 1. And that happens, of course, not on the entire manifold X, but only in a neighborhood of M so all the points such that the distance to M is at most d over 2. Or in other words, it's a neighborhood of with d. And then the statement is that the scalar curvature actually must be negative somewhere else. And I can also precisely tell you how negative it has to be, or at least how negative it has to be. So the infimum of the scalar curvature over the entire manifold X is bounded below by this function here, which is negative, and where here the constant d that we chose appears. And maybe note that this here, sort of this expression here goes to minus infinity if you approach the constant 2 pi over n. Okay, sort of that's the statement, and I guess maybe the idea is this. So you have some manifold, and maybe this has some topology here, who knows? And here you have some submanifold M in X, so the whole thing is X. And here in a sort of neighborhood of with D, you have scalar curvature bounded below by n times n minus 1. This happens here. And then the statement is, as I said, that the scalar curvature as a whole somewhere must become negative, and the infimum is bounded above by this. And of course, this means that this must be achieved or must be approximated somewhere on the outside, because here I have assumed that it's positive. Okay, sort of that's the statement of the main theorem, or that's sort of the idea. So here I know how positive it is for some time. I also know sort of how wide it is here, and then I can tell you there must be some point somewhere else where it sort of approximates this number from below. All right, and now I mentioned these conjectures before, and of course this result should have to do something with these conjectures, and in fact it does. So I claim that this result actually implies all three of these conjectures. So if you have a closed spin manifold such that this Rosenberg index is non-zero, then first of all, we can deduce that every metric on M cross the interval of this lower scalar curvature bound satisfies that the distance between the boundary components is at most 2 pi over n. And in fact, it must be a strict inequality here. So that this I've claimed that this is a corollary of the theorem. And how do you do this? So maybe if I just go back here and I look at M cross the interval, and I have some metric G here, then what I can do, I can just extend this to a complete metric on, and so, yeah, suppose here we have scalar curvature bounded below by n times n minus 1. Then I can extend G to a complete metric G bar. And I can also do this such that it has bounded geometry. Yeah, I can, since the sort of the blue part here is some compact thing, I can just in finite time homotop that to a product metric and then continue like a cylinder at infinity. And so that metric basically only varies on a compact part, and then for sure this will have bounded geometry. But now if I assume that the width is larger than 2 pi over n, then I can conclude, or from the theorem I could conclude that the infimum of the scalar curvature of G bar must be minus infinity. But now that's a contradiction to the assumption that I had bounded geometry. So I just cannot have that the width here sort of that this width here is 2 pi over n or larger, because then however I no matter how I continue, the theorem would tell me that the infimum of the scalar curvature must be minus infinity. But for sure, if the metric lives until the boundary, I can continue it in a way where the infimum is bounded below by some negative negative constant. So that tells me why sort of the first part of the corollary holds. And so that's that. The second part is sort of more or less an immediate consequence of the theorem, because if it has positive scalar curvature, then in some compact region it has uniformly positive scalar curvature, and then the theorem by rescaling tells me that it must be negative somewhere else. So that's a sort of an immediate consequence of the theorem. And the third thing is a little trick. So the third thing actually is a consequence of the first part of the corollary. So here, so just make a new page. So here, how to do this? Here you look at a large annulus in R2, and if you have a complete metric on M cross R2, then you can get an annulus times M. So you look at sort of that times M inside R2 times M. And now if you have a complete metric here, you find this annulus here, which looks like M cross S1 cross an interval. And if you have a complete metric here, then you can take a sort of very large annulus and get this width here as large as you want. And so you can get this width here as large as you want. And then you can apply the sort of first part of the corollary to M cross S1. And you still have to check that this index invariant survives after taking the product of S1, but it does. And then you see that this sort of third part is a sort of consequence of the first part. So for that reason, all these three conjectures follow for these manifolds from this one theorem. And in particular, these conjectures hold whenever the fundamental group is trivial and the dimension is at least 5 using the theorem of Stolz. And also, yeah, you can plug in your favorite exotic sphere with non-vanishing alpha invariant if you want. And then you see that you get this kind of estimates here. And they indeed really depend on the sort of differentiable structure as well. Maybe some history on these results. So they are sort of, except for the first thing, are not new. So the first thing is something that I proved a bit more than a year ago with a sort of different kind of constant here. So in the first approach that I had, my constant was not optimal. I had something else rather than 2 pi. And this was beginning of this year improved by Simone Cecchini to 2 pi here. And now this result that I mentioned, or this approach that I'll mention today, slightly improves this because it improves the inequality, this inequality here, which was non-strict before, to a strict inequality. The second statement, that's the way I stated it here, also appears in a different paper of Cecchini from 2016. And the third result that in this way here is implicit in some work of Hanke, Papa, and Schick from 2014. Okay, so this is just a summary that sort of this quantitative statement we have here implies this sort of slightly more qualitative conjectures. Okay, and I think I still have a little bit of time, and then I can sketch the proof of the main theorem. So how do we do this? So first of all, we can assume without loss of generality that the fundamental groups are actually the same. So by passing to some covering of X. maybe so that you see what's happening. Copy this to here. So if you assume this, then this M will actually be a partitioning hypersurface. So it will split the manifold into two parts. And as usual in such a situation, we take the signed distance function to the manifold M. So you put a negative sign if you're here, put a positive sign if you're here, and otherwise you just, well, you take the distance and you put the signs depending on where you are. And now we want to do index theory on this manifold X. And the problem is, if it's non-compact, then you cannot just take the Dirac operator and expect it to have an index in the completely classical sense, because the manifold is non-compact. Of course, you can do coarse index theory and define a coarse index or something like this. But that's not what we're going to do here. Instead, we're going to take this Dirac operator and modify it by some potential and make it Fredholm in this way. And first of all, I would just take my distance function as a potential, but it will be convenient to modify this distance function a little bit further. And for this reason, I choose some non-decreasing function f from the real line to itself that will be chosen later. And we consider the operator, the Dirac operator plus as a potential f composed of x. And I also need an additional chirality operator that anti-commutes with the Dirac operator. So what I want to do is, if I kind of have the spinor bundle of X, and I want to tensor that with the Clifford algebra CL01, and then this epsilon here is just the generator of this Clifford algebra. And over sort of this bundle, I consider the operator. And if I do this, I can now, first of all, show that this it's known that in good cases, this operator B will be Fredholm, because you can compute the square of it. And what you get is you get the square of the Dirac, you get the square of the potential, and then you get some mixed terms. But because this anti-commutation property, here you will get the commutator of f of x, well, I guess the other way around, commutator of the Dirac with f of x. And I guess we also have an epsilon, and that was missing here. And that is just a principal symbol of the Dirac operator applied to the derivative of f of x. And you can write this as Clifford multiplication with the differential of the distance function. And then here you get the derivative of f as well. And since I assume well, I guess since this is a distance function, this derivative here is gonna have norm 1, or norm at most 1 at least, and then I can bound this term here below by -1, and that's what I get here. So in the end, I get a lower bound of this operator b squared by the Dirac operator squared plus a differential expression involving the potential. And it looks like this. So it's the potential squared minus the derivative. And first of all, if this function is bounded below by a positive constant at infinity, then it's sort of a standard result that this operator B is going to be Fredholm. And I didn't mention this here, but of course this, if you have some bundle of some, if you twist it with a flat bundle, even if that's a bundle of Hilbert modules, this carries through, and it's going to be Fredholm in the right kind of sense. And you have some index theorem for this situation, which I think it makes sense to call this partitioned manifold index theorem, although there's sort of many variants of this. And it states that whenever you have this statement, you will have that the index of this B is going to be the same as the index of the hypersurface. And now the assumption is that the index of this hypersurface is non-zero. And now you can continue working with this in the following way. So we sort of continue working with this lower bound here. How do we do this? So first of all, the Dirac operator using the Schrödinger-Lichner-Robic formula is going to be bounded below by the scalar curvature over 4. Yeah, that's the Schrödinger-Lichner-Robic formula. And there is a slight improvement of this, which goes back to some eigenvalue estimates of Thomas Friedrich, which tell you that actually you can improve this by a factor of n times n minus 1. But in any case, you have this, and this is important to have to get the right formulas, but the sort of basic idea is that you have a lower bound of this involving the scalar curvature. And then you combining this with what I had on the previous slide, you obtain this lower bound here for the operator for B squared, which is now a lower bound in terms of the multiplication operator corresponding to some function. And this function is the scalar curvature term plus some differential expression involving the potential. And now if we assume, which we have done, that this index here is non-zero, or which we obtained from the partitioned manifold index theorem, then this implies that this lower bound here, which is a function on the manifold, cannot be uniformly positive, because if it was, then the B would be invertible everywhere and the index would be 0. So from this we can conclude that this expression here cannot be uniformly positive. In other words, the infimum taken over the entire manifold X must be bounded above by 0. And now the sort of idea in the end is that you can choose a suitable function f such that you get the desired bound on the scalar curvature. So you can choose a function f such that in the end here this tangent expression appears. And it's a bit annoying to do this, but if you sort of only try to think about it only sort of approximatively, it's kind of clear what happens. So the idea is that I have this lower bound here by the Dirac operator squared and this expression here, and here I have the scalar curvature term. And so this guy I can sort of bound below by the scalar curvature term. This is what I've written here. And if I have a scalar curvature bound of n times n minus 1, this will correspond to a lower bound of n squared over 4 here. And now the idea is I can take my potential in such a way that I sort of almost destroy my lower bound, but not quite. So I will choose my f in such a way that I sort of almost, but not quite, get this expression to be equal of to E equal to minus n squared over 4, so that I can sort of almost, well, this is sort of admits a lower bound, which is almost 0 in a way. And I don't do it quite like that. I leave a little bit of room such that it's still positive. So maybe I should write that this is sort of bound below by some constant, but which is almost 0 but positive. And now, if I want to achieve minus n squared over 4 here, then I can again solve a differential differential equation, and it will yield this function here, which is this tangent function here. And now what I do is I take f to be this tangent function here, or let's say approximately that, as long as I have the scalar curvature bound. So this is the region where I have the scalar curvature bound, and there I put this tangent function. And then once I don't have a scalar curvature bound anymore, I stop and I just continue constantly. And then I can arrange this in such a way that I get a positive lower bound on this operator here. And let's say I get a positive lower bound here. So this observation here that the infimum is at most 0, then will imply that the scalar curvature must be at least as negative as the square up to some constants of the level I achieved here. So in a way, because I have here a positive lower bound on the scalar curvature, I have some time to let this expression to be negative, and which allows me to grow my potential for some time. And the more scalar curvature lower bound I have, or the more time I have, I can let this potential grow higher. And in the end, it's gonna tell me that this, whatever I achieve in the end, must be compensated in the negative way by the scalar curvature, and that's what gives me the result. All right, that's sort of the proof sketch here. And of course, maybe this function here is not smooth and things like that, but I can work around that. And I think at this point, I'd like to stop and thank you for your attention.
Thank you. Are there any questions or comments?
I'd just like to say that partition manifold is the most beautiful partition manifold I've ever seen. I've seen hundreds of talks with this picture, but that's the best by far. You should put that on a T-shirt.
This one?
Yes.
You should okay. Yeah, patent. Yeah.
All right.
I agree.
Any other comments or questions? Well, let's thank Rudi again for a beautiful talk.
Thanks.
Thank you.